So yesterday we had discussed about um, you know the examples of registers, and we had looked at the universal shift register as well, right? Where this universal shift register can be used for multiple purpose. It can be used for hold, shift right, shift left, parallel load operations. Okay, so based on this concept, okay, based on the universal shift register concept, we can actually design any register, and the problem could be of anything as that sort. Sometimes instead of hold here, I might ask you to for 0 0, I might tell you to use shift right. Okay, and sometimes instead of shift left, I may tell you to do the operation of parallel load. Okay, so the only thing that we'll have to do here is we have to play around with the inputs here. Okay, the inputs which are given to the multiplexers. So once this is fine, okay, then it's going to be easy for us to try and understand as to how these loops are created and how these loops are connected. So I hope we are clear till this point. That is what we had discussed so far. And this is going to be your standard format. Okay, or I can say it is going to be your IC form of universal shift register. Okay, wherein you have S1, S0. Okay, then inputs A, B, C, D, then clock, clear, and the outputs in the form of Q, A, B, C, D. Okay, so in the form of IC, right? So the next one that we will be looking into is the registers. In fact, we saw this yesterday as to how the registers are incorporated for the clear facility. So in order to do that, I will take the help of my AND gate. Okay, so if in case a 0 is given here, okay, since it's an AND gate, what is going to happen if I use a 0 here, then whatever input that I'm going to give here, okay, this is not at all considered because it's a 0 here, and I will always get a 0. So which means it's a clear. Suppose in the other case, if I use 1, okay, if I use 1 here, which means the shift operation is going to happen. So whatever input I give here, okay, let's say I give 1. So 1 into 1 is 1. So 1 comes here. Okay, and my clock is as usual connected in common. Okay, all this is commonly connected, the clock lines, right? So these clock lines are commonly connected. So which means I'm making the use of this AND gate, okay, wherein if one of the inputs are 0, then the output ultimately is going to be 0. So that is the importance of having an AND gate. So if in case I do not give a 0, I give a 1, then it will take my serial input. Okay, so any doubts here, students, as to how this is done? Any doubts, please ask. If not, we can proceed. We had discussed this yesterday as well. Any doubts here? Can I proceed?
Yes, sir.
Okay, fine. Thank you for the response. Now, we will move on to the next problem, okay, which is with regards to the registers. Yes, yesterday I had just given you all a kind of introduction as to what kind of problem that we will be solving, right? So as I told you previously, right, I will be changing the operations here. So when I say I change the operations, which means it is my desire, okay, as per my wish, I will give whatever points are needed here, whatever operations are needed, okay. So as usual, I have 0 0 as hold. So hold means it is holding on to the value, which means it doesn't pass on to the next flip-flop, right? Ultimately, we are studying about registers. So what are registers? Registers are nothing but a combination of flip-flops, right? So flip-flops together, work as registers, right? So now our problem is to design a 4-bit register using positive edge. Now keep in mind we are using a positive edge clock, and they've told us to use a D flip-flop, okay, to do this operation, okay, and they want us to perform these operations, okay, which is on the right hand side. Fine. So as discussed yesterday, we will be making use of our universal shift register, right? And we will be performing the operation, right? So the first one says 00, which is hold, right? So when I say hold, then which means the value should be held. So in order for the value to be held, okay, so let us take D naught. 00 means what? 00 means A1, A0 is our select lines, right? These are our select lines, okay, and these are our inputs, our D0, 1, 2, 3. These are all our inputs, okay. Fine. So now we will see and try and understand as to how this is actually functioning. Now, when I say 00, which means the value should be held. So 00 means what? D naught should be connected. So whatever input D has, that will pass to QA, and it is actually forming a loop. Okay. It is again connected to D naught. So which means the value is actually held, and then it comes to F. So there is a loop that is getting created, right? So I hope you have understood as to how this hold function works, right? So how this hold function works. Now let us go back, okay, and we will see for 1 1 what is going to be our operation, right? So for 0 0, that is the 0 0 is done. Next 0 1 is synchronous clear, okay, synchronous clear. So which means D1 is going to be selected. So when I say synchronous clear, so I can give my inputs here. Okay. So directly I can give my inputs here. Okay. I can directly give them as 0. So if I give my 0 here, then what is going to happen? That 0 will pass. It will come to F. And the output here is again getting into my D. D will again get into Q. So which means this is also going to be 0, 0, 0, and 0 accordingly, right? Because I am selecting which one? I am selecting D1, and across D1 I am giving 0. So synchronous clear operation is also performed, okay. So what is the next one that we have for the next case is complement the contents. So can someone tell me how can we perform this task, complementing the contents? Can someone unmute and respond? Hold you have seen, synchronous clear you have seen, right? Now complementing contents, how can we do it? Is there any option for us to complement the contents? Manoj, Manoj, you can unmute and respond. Manoj Kumar S. Anybody wants to answer that question as to how we can complement the contents? Okay. So complementing the contents becomes easier when we think of the outputs, right? We have Q and Q bar. So if I take Q bar, then that is nothing but my complementing the contents. Okay. So let us see. Uh, so D2. Okay. So here you can see 1 0, 0 1 2 3, right? So 2, this is referring to D2. So D2 should be actually connected to the complemented version, right? So just check, is my D2 connected to my complemented output, right? So it is connected here to QA bar. So this comes here to D2. So D2 finally is the output function. This is the line that gets selected. So ultimately, I am complementing the contents with the connection of D2, right? Similarly, here also you can see the same connection happening, right? So even in QC, rather to say QC bar, then QD bar as well, right? So D2 is your input, this is the line selected. It comes out as a function, and this function finally becomes the input to the D flip-flop. So we were able to achieve, hold value using D naught. We were able to do synchronous clear with the help of D1, and now we are able to do the reversing of contents with the help of D2. Now let us see the next operation as to how it is performed. Okay. So 1 is nothing but your circular shift right. So what is the difference between shift right and circular shift right? Can someone tell me? Difference between shift right and circular shift right. What's the difference?
So in shift right, once we move the bits to the right hand side, the leftmost bit is not considered anymore.
Okay.
And in circular shift, the last
Rather
bit
to
comes and
say,
takes the place.
it is actually occupied by zeros. Okay, the leftmost bits will be occupied by zeros, and yeah, go on.
Yes, sir. So in circular shift right, the rightmost bit will come and occupy the left bit place.
Yes, so once it is shifted, okay, as the number of bits are shifted, it actually comes and sits towards the left hand side. So this is how, thank you. So this is how your circular shift right happens. So which means what we have to do, we have to actually go and take the last bit, okay, which is at the extreme right hand side, and connect it, okay, towards the leftmost flip flop. Okay, so we will see how it is done, right? So if I am selecting D3, okay, D3 is my circular shift right. So D3 should actually be connected, okay, to my extreme rightmost bit, which is QD. Okay. So once this comes here, okay, this is actually, just assume the bit is traveling through, okay, and then the select line gives us as D3. So D3 output comes here to my function, and then finally it gets into my flip-flop. And then it keeps shifting one after the other, okay, as you all know, right? Data gets shifted one after the other. So it comes here to QA, right? So the value comes to QA, and then this value comes here to D3, right? Comes to D3, and from D3 it comes here to QB. Then this QB is actually connected to D3. So once this is connected to D3, right? So this will get inside, and then it comes across QC, and finally this is coming here to the final flip-flop, right? The final flip-flop, and then it gets in here. So ultimately what is happening? You can see that the final bit, okay, is actually traveling across, and we are giving as a feedback and giving to the first multiplexer. And with this path, okay, with this path, it is able to travel through, okay, it is able to travel through all these flip-flops and then come across and sit in the final one. So we can see that, uh, your problem is actually solved. So we were able to use D0, D1, D2, and D3 effectively. So ultimately what you have to do, You have to read the problem properly. You have to see what is given in the truth table and accordingly decide as to how your connections are going to be. Okay, so they have told you to use a D flip-flop. Okay, so make sure you use a D flip-flop. Okay, sometimes, many times I've seen students making this mistake. If they tell you to use T flip-flop, they would have written D inside, okay, wherein you'll be losing some marks. Say if the question is for about 10 marks and then you do everything properly, but then if the naming is not fine, okay, then this you there might be chances of you losing slight marks. Okay, any doubts here, students? Can I continue? Any doubts here? You can ask. Yes, can I move on?
Yes, sir.
Okay, thank you, Rohit. So having understood all of this, all about the registers, about serial in, serial out, parallel in, parallel out, serial in, parallel out, parallel in, serial out. Okay, so all these and the universal shift registers and how problems can come across. Okay, how we can solve those problems and solutions to these problems. We will move into the other topic. This is all about the explanation, right, as to how it is getting done. I have kept it here for your reference, right, so that you can actually go through the content. So the next that we will be looking on to is counters, right? And can someone tell me where do we use counters in our day-to-day applications? Do we use it or not?
So stopwatch.
Yes, stopwatch, very good. And then where else can we use counters?
A clock, sir.
Clock, very good. And then don't you think we use it in the traffic?
Yes, sir, for the signals.
Yeah, yes, for the signals, right? It will help us to down count the signals, right? So wherein if it's 50, 49, 48, it counts down and it gives us the timing. So this is the application of counter. So we will be looking into what are counters and how we study about it and how we design it in our digital electronic circuits. So counter is just an example of a register, just that you know it handles data in a different way. So which means the counting can start from a lower value to a upper value, or from a upper value to a lower value, which means it can have an ascending value or it can have a descending value. So when it has an ascending value moving from a lower value to a higher value, then I can term it as an up counter, and the other way around would be my down counter, right? So this is also a kind of register. Now again, register is a combination of flip-flops, right? Primary purpose is to produce a specified output pattern sequence, and that is also called pattern generator. So we will be exclusively solving problems, and we will try and understand as to what is this pattern generator and how patterns are generated with the help of counters and how we can design them. So we will be seeing them in the problem point of view. Each stored 0-1 combination is called the state of the counter. Now we are coming up with new terms, right? And this is called state. Now, understanding this is important because we will be looking into something called the state diagram. Okay, the state diagram, right? The total number of states is called its modulus. Okay, modulus is nothing but the total number of states. Say for example, if I count 0 0 0 1 1 0 1 1, so which means how many states does it have? How many combinations does it have? From 0 to 3, how many combinations?
Four.
Yes, 4 combinations, right? So I can say that it has 4 states and the modulus is 4. Okay, the combination of these states, the total number of states is called modulus. If a counter has m distinct states, then it is called a mod m counter. Okay. So as the number of states, so is called its mod. Okay, fine. The order in which states appear is referred to as its counting sequence. Okay, and we can actually look into this with the help of a diagram called state diagram. Okay, so what is a state diagram? A state diagram looks something like this, right? So this is how your state diagram looks. So SI, okay, SI is nothing, I is nothing but your numbers. It can start from 1, 2, 3, or sometimes, we start with even 0. Okay, state 0, 0, 1, 2, 3, and so on. It keeps going. So these arrows that you see, okay, these arrows that you see is actually telling us from S1, state 1, it is moving to state 2. From state 3, it's going to state 4. From state 4, it just moves on, and I've just generally put it as SM. Okay, a general state, or it could be any state. So I hope this diagram is understood as to how these states are represented. Any doubts here? Okay,
No, sir.
fine. If there is no doubts, then we will proceed and we'll try and understand. So the first counter, okay, that we'll be looking into is the binary counter. So I call it binary counter because it has zeros and ones, right? So binary, two values, and it will be having a ripple effect. Ripple effect is nothing but, when you throw a stone on the water body, okay, probably a lake or something, you can see the ripples occurring, right? So the first ripple, and then it passes on to the next level and to the next level and so on till the energy is available. Once the energy is exhausted, the ripple is also not seen, right? So counters whose counting sequence corresponds to that of binary numbers are called binary counters. So as I told you, if the counting is with respect to binary numbers, then I call them as binary counters, right? So modulus is 2 raised to n, where n is the number of flip-flops in the counter. So how many flip-flops will I need will be dependent on the value of n, okay, where the modulus, okay, the number of states is 2 raised to n. Binary up counter, binary down counter. So these are some of the examples that we can look into, right? So the next one that we will be seeing is 4-bit binary ripple counter. So we will take 4-bit. So as I told you, the number of bits will be the number of flip-flops. So here it is 4, which means I'll be having 4 flip-flops. 1, 2, 3, 4. So I have 4 flip-flops, right? Okay. So this is nothing but representing your T flip-flop. Okay, instead of we representing in this fashion, okay, in the horizontal fashion, we are actually representing in the vertical fashion. And the clock pulses, okay, if you can see the clock, initially only it is given, and then the rest of the clock is dependent on the q bar output. Okay, so this kind of representation where the clock is dependent on, okay, where the clock is enabled by the complemented version of the previous flip-flop is called asynchronous. Keep in mind, it is asynchronous. Okay, the flip-flop is constructed by connecting together J and K terminals of a positive edge-triggered JK flip-flop and labeling this common terminals as T. So I think you can recall, right? So how we have converted our JK to T flip-flop, right? Or how the T flip-flop looks. So T flip-flop is nothing but shorting both J and K. So it becomes a T flip-flop. Okay, so that is what I have put up here for your um, understanding. Each positive transition from logic 0 to logic 1 causes the flip-flop to toggle. Okay. So as you all know, the T flip-flop, when it's having 1, then whatever input was there, okay, that is going to be toggled. But if it's a 0, if t is equal to 0, then whatever is the output, the same thing will be in the next state as well, right? So this is how your truth table of your T flip-flop is. Now let us take, or you consider this counting sequence here where I have Q naught, 1, 2, and Q3, right? So these are all nothing but our outputs here, okay? Q naught, Q1, Q2, Q3, Q naught, Q1, Q2, Q3. So as usual, I will take my 4-bit combination, okay, which is 4 zeros to 4 ones. So after 4 ones, it should actually give me 4 zeros, right? So how do we do it? We actually connect, okay, T, all the T's are connected, okay, all the T's are connected, and then given to something called count enable. So count enable is nothing but, it is like a high value that is given, okay, and then it keeps passing on whatever value you give here, okay. If you give 1, then yes, 1 is passed, okay. Then if you give 0, then 0 is passed to T. So all these are connected in parallel. But then for this value to be passed to the next level, we need the clock to be enabled. So if the clock is to be enabled, then the output from Q bar should be actually high. So it will wait for till the Q is high, and then this is enabled. Okay, the same explanation applies for the other two flip-flops as well. So it should have a high value here, then only it is enabled. So the values here, okay, will pass on to the next level only if these flip-flops are enabled. Okay, fine. So as you can see that, it takes time for the value to pass from one point to another point. So let us say I have given a value here as count enable, okay, say 1. So 1 is coming here, okay, but 0 is here, and then 0 means it is getting disabled, okay. So this 1 is here, so 1 will not come here, okay. So it is waiting for uh, the enabling. So in the next step, okay, when this becomes 0, okay, when this becomes 0, so 0 comes in, 0 is here, then 1 is here, so 1, so this is enabled. Whatever was there previously, okay, previously it was 1, so that gets passed and it comes to the next flip-flop, right? So it is taking time, or it is waiting for the next clock cycle to pass from one end to the other end, from one flip-flop to the other flip-flop. So let us understand this in a proper way with the reference of a waveform. Okay. So now if you see this waveform, so these are all our count pulses. Okay, count pulses which are moving from low to high values, which means zeros and ones. So what you can do here is you can actually put a dotted line or probably a straight line and try and understand. Okay, so for our reference, what I will do is I will just have the count of the clock. Okay, so I will take the high values alone: 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. Okay. Now, if you cleanly observe, okay, if you can observe properly, now Q naught gets active at the first clock pulse, okay, and Q1 will be in the same state as Q naught till the second clock pulse, okay, and Q2 will be in the same state as Q1, okay, till the fourth clock pulse. Q3 will be the same state as Q2, okay, till the eighth clock pulse. So can someone tell me what about Q4? Suppose I add Q4 here. Okay, Q4. So when will Q4 become high? When will it turn from low value to high value? At which clock pulse?
16.
Exactly, that is right. So at 16th clock pulse, okay, the next one is actually going to change. So you can see here, so it is 1 and then 2, then 4, then 8. So it's like 8, 4, 2, 1, right? So that is how it is. And then one more interesting thing that you can see here is in this uh, clock pulse, okay, in this clock pulse. So here it is 0, 0, 0, 0, okay. And in the next state, okay, so which means I'm going to take the positive clock pulse. Can someone tell me what we are going to get here? We're going to get 1, 0, 0, 0. So you can see the values like this, okay. So 0, 0, 0, 0, 0, 0, 0, 1. So 0, 1, 2. So the next value is 2, okay. So how is it 2? 0, 0, 1, 0. Understood? So this is how you can actually break up into each positive cycle, okay, and uh, put these values and understand as to how we are getting them. So ultimately we will be getting these values 0, 1, 2, 3, 4, 5, okay, up till the high value. So once the high value comes, then again we can actually reset it, and then we get the values 0, 0, 0, okay. So this is nothing but your 4-bit binary counter. So I hope you have understood this concept, right? Any doubts here? Any doubts here? Fine. So whatever was told so far, okay, I have put it in the form of explanation, okay. So you can try and understand here as to what these are, okay, referring to. Right. So quickly we will just look into the important ones. This is also known as a ripple counter, since the change in the state of Qi minus 1 flip-flop is used to toggle Qi flip-flop. So the present flip-flop will actually depend on the previous flip-flop's output. Okay. So the effect of count pulse must ripple through the counter, and ripple counters are also referred to as asynchronous, as I told you previously, asynchronous. So that's important. Okay, you have to make note of this, asynchronous. Then propagation delay. There is a propagation delay between input and output of a flip-flop, which means if you have to pass one value from the first flip-flop to the last flip-flop, then it takes a lot of time. That is because of this ripple effect that needs to happen from one point to another point, right? It has to keep passing through. So the rippling behavior affects the overall time delay between the occurrence of clock count pulse when the stabilized count appears at the output terminals. So when is the worst case? So the worst case is moving from high value to a high value, right? From high value to a high value. So that is the worst case because it has to pass through all the states. In between, I just cannot jump to a specific state. For n-stage binary ripple counter, the worst case time is n into TPD. Now this is important, where your TPD is your propagation delay associated with each flip-flop. Okay. Okay, so this is how your 4-bit ripple counter, the binary ripple counter works. Okay, where your TPD was nothing but your propagation delay, right? So the next one that we will be looking into is synchronous binary counters. So can someone tell me what is synchronous?
Which is continuous.
Which is continuous, good, and also it is connected to a clock, right? The changes in clock happens simultaneously. Okay, so count pulses are applied directly to the control inputs C of all the clock flip-flops. All flip-flops change simultaneously after appropriate propagation delay associated with a single flip-flop. Now this point is important. Change simultaneously. Okay. But then in the previous one, what was the disadvantage with our asynchronous? We were not able to change the state immediately, right? Because it had to wait for the value to go high, and then uh, so that was actually delaying the output. So just you can imagine, okay, you can imagine to pass the values. Okay, we will just get back to the waveform, right? So just give me a moment. Yeah, just to pass this values, okay, it was taking long time, right? It had to wait for a long time for the state to change. So this doesn't happen, okay, if we use a synchronous type of counter. Okay, so where it is all changing simultaneously. So let us take this as an example, okay, and you can understand as to how the same counter that we saw previously, okay, the binary counter, but then now it is synchronous. So what is the major change here? The clock. Okay, so you can see the clock is actually given in common. So all clock pulses are given in common, right? Okay, so what will happen because of this? Changes can happen simultaneously, right? Simultaneously changes can happen. Okay, now there is an interesting thing here, okay, where the count enable is also connected to my AND gate. So if my count enable is 0, okay, so which means 0 directly gets in here, and then here also it is 0, my output is also 0, which means my flip-flops will never work. Okay, never work means there is no data entering in, there is all only zeros, right? Okay, so now if there is a 1, if there is a 1, then 1 is going through, and then here also I've got 1. Okay, now this 1, if I give 1 here, the same thing comes across, okay, my output. Okay, and this is 1, 1 into 1 is 1, right? So 1, so it again passes through. Now you should understand, okay, that this will happen at instantaneously. Okay, instantaneously the values will pass through. There is another way of actually representing this, and that is nothing just but here, if you can see to the number of inputs to your AND gates, what is happening with the number of inputs to your AND gates? Is it reducing or increasing?
So it's increasing by 1.
Yes, it's increasing, right? So what is happening here? That is because it is taking the value of Q naught. Then it should track enable. Now in the next one, what is happening? It should take this and also take this and also check as to what was the value previously in Q naught. So as your number of stages increases, your number of inputs to AND gate is increased. Now, is there any way that we can reduce these number of inputs to AND gates? Can you come up with some solution wherein I can reduce these number of inputs increasing? Can you think of it? See these number of inputs increasing in an ascending way. Can you think of these options as to how I can reduce them, how I can keep them common? Is there any way of doing it? Yeah. Okay. So what we can do here is, okay, we will just get to it in a moment. The AND gate preceding each key detects if all lower order bits are one state. Okay, so it will check if it is all in one state, then only it will actually proceed. If one of the values are 0, okay, then those values, then the whole thing is 0 here, right? So let's say if Q naught is 0, so that Q naught is also passing here, and this is also becoming 0, the last one. If yes, toggles on positive clock edge. So whenever there is a positive clock edge, whatever is the value, that's the property of T flip-flop, right? Whenever there is 1, then the value is toggled. If it is 0, the same value is continued. Okay, so one drawback here, as we have discussed, is the number of gates are actually increasing. Okay, so in order to do that, okay, in order to counter this number of gates, number of inputs increasing, okay, we can actually take the output of the previous AND gate. Okay, that's the simplest way of doing, right? Because instead of connecting two lines to the inputs here, directly take just the output of the previous AND gate. So if you just take the output, which means it is connected, okay, and you can actually make your circuit more simpler. Okay, so you can just see that all the AND gates here have two inputs. So one is getting connected here and the other one to the count enable. So if you can see the second AND gate, okay, the output is actually the result of the previous output. Okay, also it is checking for Q1. So this is one easy way of reducing the number of inputs in AND gate. Okay, fine. So now looking into mod M counter. Okay, mod M counter is nothing but having M states. Okay, M states. So which means having many states. Okay, so we will just see how this can be done with the help of JK flip-flops instead of using a T flip-flop. Okay, so M is less than 2 raised to N. Okay, so M is nothing but the number of states. Load an initial binary number prior to counting operation. So we have to give an initial value, and the counter structure is modified to allow parallel loading, just like how we saw in universal shift register. Here also we have an option to load the value in parallel. JK flip-flops are used, as I told you, instead of T flip-flops. And we have two enable signals here. The one is to load these values 0, 1, 2, 3, D0, D1, D2, D3 to load these values. And the other one is to enable the count. Okay, which means it will only count 0, 1, 2, 3, 4, 5. It will just up count or down count. So depending on what kind of count is needed. So here we will have to use an AND gate, okay, in order to perform this operation. So this is going to be your mod M counter. Okay, this whole structure is your mod M counter, and we are making use of the JK flip-flop. As I told previously, the JK flip-flop is used. Okay, so just have a look at it. in that it seems to be a complex structure, okay, but then when we try and understand each thing, okay, it becomes very simple for us, right? So now let us think of the count enable. So when I say count enable, so which means do I need to give a high value or a low value? What should I give when I want to enable something? Do I give a high value or a low value? Yes, students?
Sir, high value.
High value, right? Okay, so when I want to enable things, I will give high value here. So when I say count enable, okay, so which means this is high, and load enable, okay, load enable, I will be giving a 0 here. I'm not loading the value. So loading and counting will not happen together. Okay, it is one after the other, or I can rather say if counting is happening, then load wouldn't happen. If load happens, then count wouldn't happen. Okay, so initially what we will do is we will actually load the values. Okay, load the values to d0, d1, d2, d3, so which means count will be 0 initially, and then load will be 1. So these values gets inside, and then um, the 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 values gets computed. So now let us look at the first case where the counting operation is happening. So when I say count operation, then I give this one as high, okay, and the load enable as 0. So if I give 0 here, okay, it's going through an inverter, so which means I'll get a 1 here. So 1 and 1, so 1 is going to come here, okay, and since it's a 0 here, okay, so I'm going to get a 0 here, and 0, since it's an OR gate, I will get a 1, right? So J is 1, okay, and it will start counting. Okay, initially 0 was there, and then 1 will come, it will pass through your AND gate, the same thing. Okay, see this structure that you see here, it's all a replica here. Okay, it's all a replica, so the same operation is happening. So as usual, okay, we have the JK flip-flop. Okay, JK flip-flop. So we'll have 1, 2, 3, 4. Okay, 4 JK flip-flops. And then now can you tell me, is it synchronous or asynchronous type, this structure? Is it synchronous or asynchronous?
Synchronous.
Okay, because all the clocks are connected together, right? So all these are connected together, right? So I can call them as a synchronous structure, right? So let's take the other case. My count enable is 0, and then my load will be 1. Okay, and since I give a 1 here, okay, 1 comes and sits, and whatever value d0, d1, d2, d3, whatever values you're giving, okay, that will come and sit here. Okay, so suppose say I give 1, so 1 will come and sit here. So 1, 1, so 1 comes here, since it's a 0 here. Okay, so I get a total 0. I am not bothered of what is coming here because it's already a 0. So 0 plus 1, I will get a 1 here, right? So this is how your load operation happens, and this value will actually come in here. Okay, say 1, then this is 0, so anything here is 0. So here also I will have a 0, and this value, okay, it is actually connected to this AND gate, so this is also a 0, so which means 0 plus 0 is 0, and K is getting 0, and J is getting 1, right? Okay, so what is my final value? My Q0 will be equal to 1. Okay, JK flip-flop, if you can see the truth table, When j is 1 and k is 0, your output q naught will be 1 and your q bar is going to be 0, right? So those are again carried forward, okay, carried forward to the next AND gate, and accordingly all these structures are functional, okay. So I hope you have understood, how to access data, or how to understand the circuit. Okay, not many times this has occurred in your examination. Okay, the questions that will be asked is to design a specific counter, okay, maybe say mod 10 counter or mod 8 counter, and accordingly you will be using its functionality. Now this is our IC, okay, and this structure that you see here is the internal of this IC, okay. So all that you see here, okay, you can see that you have D naught, okay. D naught is nothing but this one here, okay, and your D1, D2, D3, okay, your load line, okay, and then your count line, then your clock is here, okay, and then all these outputs, q0, q1, q2, q3. So all these are actually here, okay. So this is an IC, okay, and the internal structure is this, right? So JK flip-flops are used to enable signals. One, to allow parallel loading. Parallel loading means to get these values inside D0, D1, D2, D3 to get these values. And second, for counting, okay. So this is for counting, as I told you, okay. The load function takes precedence over the count function due to not get connected, okay. That is because if there is a load, then the count will not happen, okay. Why will it not happen? Because of this inverter. Because if I say load enable, even if this is 1 or 0, even if the count is 1 or 0, it doesn't matter, because my inverter will always throw up a 0, right? So let's say my count is 1, okay, and I want to load the value also, okay. So what do you think is going to happen? 0 is going to come here, okay, so which means I'm going to get a 0 here. So this AND gate is as good as not functional, right? So which means the count is not happening, only the load is happening. So what can we conclude with this? We can conclude that our load enable is having higher priority than the count enable, okay. So that is what you can understand with this circuit, right? So I think students, we will stop here, okay, and then we will discuss few more concepts in our upcoming classes, okay, wherein we will try and understand as to how these mod M counters can be used for different applications. For example, mod 10, okay, an 8-bit counter, then shift registers counters, how we use shift registers, okay. So all this we will be seeing in our upcoming classes. So do you have any doubts till the concepts that we discussed so far? Are you all clear with the concepts discussed?
Yes, sir.
Okay, fine. Okay, then we will try catching up in the next class and try and understand the applications of mod M or variations of mod M.